Hi, I am a tutor in Uplatz. Today we are going to discuss about VHDL Part 1. Overview: the HDL Hardware Description Language, a language that allows description of hardware for documentation, simulation, synthesis, verification. To use an HDL, you need a CAD system that supports it. Major CAD systems support VHDL, Verilog, System C, System Verilog. CAD system, just one, some of them: Canon, Syncision, Mentorgraphics, Model Sim, Questa, Altera, Xilinx have arrangements to use Model Sim, Synopsys, mainly towards synthesis and ASIC production for from HDL descriptions. A brief history of HDL. The development of today's HDL began in 1980s. State of CAD generators and proprietary HDL. VHDL requirements set in 1981. VHDL IEEE first standard in 1987. New versions in 93, 97, 2000, 2008, and a new version is being worked on. Verilog, the first standard was in 1995. System C, first standard was in 2005. System Verilog merged with Verilog in 2009. New version in 2012. Common to all systems, HDL have source HDL file. The structure of generated file is common. Library files are for design units. Source file analysis, compile VHDL library files, simulation, synthesis. A first example, decide to do a VHDL description of a full adder. A device consists of an interface, an operational port, interface, the inputs and outputs, operational port, the functional behavior, format, entity, unit name is port class and unit name. For full adder would have entity full adder is port A, B, C in bit, sum out bit, or C out bit in full adder. Port is portion in term a port class. When specified in port class, these signals have scope over all architectures of this NCD. Signals, ports, mode styles, port ABC, yes, ABC in bit, sum out bit, C out bit. Signals named names referenced in the port class are signals. ABC in sum out, C out represent wires of the physical unit. Signals are objects that have both a value and a time component. Port modes, in this example, you have input and outputs. The port mode specifies the direction of the signal transfer and a couple of other properties of the port. Modes in signal can only be used, that is, can only be read or can only be used on the right hand side of the equation, cannot be assigned to. Out signal value can only be written, cannot be seen or used in the design as it is an output and therefore directional. In out, signal can be both written to, assigned to, and used to. However, signals of this type are connected to buses and therefore this signal mode requires the signal to be resolved. Buffer signal value can be written to go to and used internally in the design. Basic test built in part of the standard and language proper type bit. Your typical binary type with values zeros and ones. Declaration that established this type bit is 0, 1. Use of signal of type bit A assigned 0, A, B, X and Y or Z. Note that the value is either 0 or 1. Architectural design unit specifies the operational code architecture identifier of entity IDEs. Declarations begin architect the statement part and identifier architect the statement part any concurrent statement of the language. For a full adder architecture, one of full adder is begin sum A XOR B XOR C in, C out A and B or A and C in or A and B and C in, end 1. This type of description is referred to as Dataflow description. It is excellent for combination logic leaf units of a design. Consider a 4-bit adder. This hardware is modeled in VHDL. First, we'll do a Dataflow model for the unit as a whole. We'll create two alternative data flow models. Then we'll create a structural model where the leaf units are basic gates. And now we are considering a 4-bit adder with carry in A0, B0, A1, B1, A2, B2, A3, B3, and some ones, some 0, some 1, some 2, some 3, and C out as output. And intermediate carry are passed on from each block to the other block. A multi-bit adder example will model using a data flow style, bit vectors for the ports and individual signals internally, bit vectors for ports and bit vectors internally. The entity design unit same for both. Entity MB adder is port A, comma B, in bit vector 3 down to 0, C in bit, C out bit, sum out bit vector 3 down to 0, and MB adder. Architecture 1 of MB is signal C bit vector 4 down to 0. Begin C of 0 is Cn, sum of 0 is equal to A of 0 XR B of 0 XR C of 0. Sum of 1 is equal to A of 1 XR B of 1 XR C of 1. Sum of 2 is equal to A2 XR B2 XR C of 2. Sum of 3 is A3 XR B3 XR C3. C1 is equal to A0 and B0, or A0 and C0, or A0 B0 and C0. C2 is equal to A1 and B1, or A1 and C1, or B1 and C1. C3 is equal to A2 and B2, or A2 and C2, or B2 and C2. C4 is equal to A4 and B3, or A3 and B3, C3 and B3 and C3. C out is equal to C4 and 1. Data flow architecture. Data flow architecture should be limited to leaf units. The level of complexity should be limited. The 4-bit adder is not bearing, but much more than this should be avoided. Probably want to limit data flow description to 30 or so late. Data flow architecture synthesis extremely level across most synthesis to Altera, Xilinx, synopsis, metagraphics. The second data flow architecture 2 of MB adder is signal C bit vector 4 down to 0. Begin C0 is equal to C in, sum A XR B XR C 3 down to 0. C4 down to 0 is equal to A 3 down to 0 and B 3 down to 0, or A 3 down to 0 and C 3 down to 0, or B C 3 down to 0, C down to 0, C out is equal to C4 and 2. Now the power of this HDL specification. Now the power of the HDL expression. They carry ripples through repeated evaluations of the equation, as whenever a signal on the right hand side changes, the equation is re-evaluated and the new value scheduled for the assignment to the signal. Also synthesizes well. Operation on type bit. Consider the following declaration: signal XY bit. Logic operation X and Y, allow shift operation X or Y, arithmetic shift SR ASL, X NAND Y, X NOR Y, logic shift SR LSL, X or Y, X NOR Y, not Y. These are work on vectors. Note for logical expressions, the equation is only evaluated until the result is determined. Assignment and relation operators. Assignment operators for signal for variable. Relation operators X equal to Y, X not equal to Y, X less than or equal to Y, X greater than or equal to Y. Example of use: X is equal to 1 and Y equal to 0. VHDL structural example. Again, consider the full adder. Before doing a structural description, must have the components that are going to be wired together. They must first be written and compiled into the library. Only the entities are given. Each would have an architecture. Entity and 2 is port A, comma B in bit is an out bit. And 2. Entity XR2 is port A, comma B in bit is an out bit XR2. Entity R3 is port A, comma B, comma C in bit is an out bit, and R3. The AND and OR gates and two entity and this port A, comma B, N bit, Z out bit, and to architecture of one of and 2 years begin Z A and B after 2 nanosecond and 1. R3 entity R3 port A, B, C in bit, Z out bit, and the architecture one of R3 is begin Z is assigned A or B or C after 2 nanoseconds and 1. Structural example of full array. The first part architecture structure of full arrays must declare the components that are used, components and to port A and B in bit instead of bit, and component a component XR2 port A and B N bit instead of bit, and component R3 port A, B and C in bit instead of bit, in component state which library to find them in which they are to use for all and to use entity work and to give them for all XR2 use entity work dot XR2 behavioral for all R3 use entity work R3 behavioral declare local signals required signal additional CT1, CT2, CT3 bit. The second part of the architecture from the begin wire up XOR gates for A XOR B XOR C in G1 is equal to G1 XOR2 port map A comma B comma ADDT G2 XOR2 port map ADDT C in sum wire up the count G3 and 2 port map AB CT1 G4 and 2 port map AC in CT2, G5 and 2 port map ABC in CT3, G6 or 3 port map CT1, CT2, CT3, and CO end structural. Multibit header can use the structural full header to wire up multibit header. The entity design unit MP header is port A comma B in bit better 3.0, C in bit, C out of bit. Sum of bit vector 3 down to 0 and MB error entity is same as before. Architecture structure of MBD arrays must declare the components that are used. Component full error port A, B, C in bit, sum output, C out bit and component for all full error use entity work full adder structural signal IC1, IC2, IC3 bit begin U0 full adder A0, B0, Cn sum not sum of 0 IC1 U1 full adder A1, B1, IC1 sum 1 IC2 U2 full adder A2, B2 IC2 sum 2 IC3 U3 full adder A3, B3 IC3 sum 3 Cout end structural. Summary. A note on which VHDL said the data flow state synthesis as well, the structural state synthesis as well, seen several initial examples of VHDL code. We will now focus on that part of the language for small data flow and state machine designs, pick a problem. VHDL data types, VHDL numerous comparable to modern high-level languages. The one useful for synthesis will be highlighted. Predefined the bit type bit, a predefined type with value 0 and 1. Declaration type bit is 0, 1. Type bit, a predefined type with a value of 0 and 1. Declaration type bit is 0, 1. An enumeration type bit, a list of possible values. The elements of the list are in single S, if it's a single element, if more than one character than numbers S. Also predefined type boolean is false, comma true. Enumeration type predefined type bit and boolean. Enumeration type initialize the leftmost element of the set for the signals and variables declared to be of the type. Other examples used user-defined type of code OP0, OP1, OPR, OPN, OP not, OPR, XR, OP, XNOR, OP add, OP sub, OP increment, OP decrement, signal instruction for code, variable my bit. Integer type integer range is at least 32 bit to use complement, character, type character, single, ASCII character, real numbers, type real, floating type, IEEE standard. Predefined type time is range of 0 to 1E18. Units FS femtosecond, PS 1000 FS is equal to picosecond, NS 1000 PS is equal to nanosecond, US 1000 NS is equal to microsecond, MS 1000 US is equal to millisecond, SEC is equal to 1000 millisecond, second, minute is equal to 60 seconds is equal to minute, and units. Use predefined, the distance is the range 0 to 1 e power 16, A Ashram base unit, enum 10A nanometer, mil 25,000, 2,54,000 A mil, inch 1000 mil inch, and units. Usage variable X, distance variable Y, time. X is equal to 5A plus 14 inch minus 45 mil. Y is equal to 3 nanosecond plus 5 minute. Any implementation allows for declaration of physical types, the range of 21474836472 to minus 21474836472 plus 21474836447. Subtype pause init is range 1 to integer I. Variable MRI pause init is a subtype of type is of the type. Note VHDL code is case insensitive. Subtype pause init is range 1 to integer is the same as the declaration above. Composite type arrays, the type my word is array 0 to 31 of bit. Type register is array 7 down to 0 of my word. Unconstrained array, type memory is array integer of my word. Use variable my mem memory 0 to 65 536. Predefined array, subtypes positive is integer, range 1 to integer I. Integer I is the largest integer for this iteration. Type string is array, positive range of character. Subtype is natural, is integer, range 0 to integer I. Type bit vector is array, natural, range of bit. Examples of use, variable message string 1 to 17. This is a message. Text inside a string is case sensitive. Message 1 to 16, modified message within double quotes. What would be contained in the variable message? Signal low byte bit vector 0 to 7. Signal F word bit vector 15 down to 0. Other types, common types, records, dynamic records, access types, file IO, file types. Declaration signals for use in entities, architectures, procedures, functions, and process. Scope depends upon where declare can be sought of global scope of architecture. Have a value and time component. Assignments do not take place immediately. Assignment of new values are scheduled. Declaration in entities, architecture, concurrent process. Signal by SIG bit is equal to 1. Signal by integer is equal to 45. Variables for use in processes, procedures, and functions. Scope limited to process, procedure, or function in which declare cannot be declared in declarative regions of architecture. I have no limit component. Any assignment take place immediately upon assignment. Variable may where bit, sometimes used in synthesis. Analyzes signal real num bit vector 0 to 31. Analyzes signal bit is real number 0. Analyze exp bit vector 0 to 7 is real number 1 to 8. Analyze fract bit vector 0 to 23 is real number 9 to 31. Then in the design you can assign or use any of the names real number sign exp fract. Constants pi real 3.141592. Constant cycle time 7.9 nanosecond can be declared and used, cannot be assigned to component. Declaration needed for hierarchical model. Component local component name, port declaration from component entity and component. The easy way to do a component declaration is to copy the entity declaration and change entity to component. Delete the ease and the change any accesses to any component. Once declared, the component must be configured. Operations, logical operators, and or NAND, NOR, XOR, NOR, not apply to types bit and boolean. The relational operators dot equal to are not equal to less than or equal to greater than equal to result of comparison with the relation operators boolean. Adding operators plus minus and plus and minus work with real and integer types, and its concatenation operator works with types bit and bit vector. Result and find is concatenation of the plus, right? X is equal to 0, 0, y is equal to 1, 1, 1. Result x and y would have value 0, 0, 0, 1, 1, 1. Scheduled for assignment. Variable concatenation example, variable r comma x bit vector 13 down to 0, variable y bit vector 13 0 down to 1, signals s p val with signal q76 bit vector. Using part of the vector is termed slicing, or 15 down to 0 is equal to x 13 down to 24 and y 0 to 7, or 31 down to 30 is s and p value. Q76 R and S and P value. How large does Q76 have to be? Size of Q76, size of concatenated must match the size of the target. Q76 could be part of the 0 to 30 or 33 down to 0. More operators plus minus multiplying star division, mod REM star and division can be used for integer and real. Mod and REM are value only for integer type. Miscellaneous star absolute not. Concurrent statements. Concurrent statements are those that can appear between the beginning and end of an architecture. With these statements, you model the component or the system to be modeled. These statements have semantic meaning and execute independent of the order in which they appear in the model. These statements Boolean equations synthesize well. Component concurrent statement and how structural architectures are created as well. Component instantiation statement prior to use the component must be declared and configured in the declarative region of the architecture. Label component generic map aspect, port mat aspect. For all component name, use entity work dot component name architecture name. Consider that the following is already analyzed and in your library. Entity widget is port P1, P2 in bit in widget. Architecture Y of widget is architecture is raw widget is. Declaration of component architecture use it of XYZ is component widget port P1, P2 in bit in component, and the configuration is for CO widget use entity work dot widget Y. For others, widget use entity work dot widget Z. Note that the component declaration is the same as the entity declaration, except that entity becomes component and it is end component. Instantiation signal ABCD bit begin CO widget port map A, B, C1 widget port map P1 to C, P2 to D. What about repetitive structures? When we have repetitive structures to build up with instantiations, generative statement automates the instantiation of repetitive structures, leftmost unit, inner unit, and rightmost unit. Entity bit comparator is port A, B, GT equal to less than in bit, A greater than B, A equal to B, A less than B out bit, and bit comparator, or there's a bit comparison or of bit comparator is begin A greater than B is assigned 1 when A is greater than B or A is equal to B or and greater else 0. A equal to B is equal to 1, A is equal to B and equal else 0. A less than B is assigned 1 when A is less than B or A is equal to B and less than else 0. And bit component architecture diagram is shown there. The multi-bit comparator entity byte comparator is A port A, B bit 7 down to 0, A and B and data greater than equal to less than in bit previous slice results. A greater than B, A equal to B, A less than B outputs and byte comparator. Now we will look at three possible approaches to implement this. The first is, of course, 8-component instantiation. Start of architecture iterative byte comparator is 2-component declaration configuration component bit comparator port A B greater than equal to less than in bit A greater than B, A equal to B, A less than B of bit. In component for all bit comparator use entity work bit comparator bit comparator architecture. Internal signal to connect with position signal. IGT I equal ILT bit vector 0 to 6. Component instantiation begin C0 bit comparator port map A0 B0 GT equal to less than IGT equal to 0, I equal 0, ILT 0. C1 bit comparator port map A of 1 B of 1 IGT of 0, IG equal of 0, I less than 0, I greater than 0, I equal to 1, I less than 1. C2 bit comparator port map A2 B2 IGT 1 I equal to 1 ILT1 IGT 1 I equal to 2 ILT2. C3 bit comparator port map A3 B3 IGT equal to 2 I equal to 2 ILT2 IGT 3 I equal to 2 ILT3. C4 bit comparator A4 B4 IGT3 I equal to 3 ILT3 IGT4 I equal to 4 ILT4. C5 comparator port map A5 B5 IGT4 I equal to 4 ILT4 IGT5 I equal to 5 I less than 5. C6 bit comparator port map IA6 basic I greater than 5 I equal to 5 I less than 5 I greater than 6 I equal to 6 I less than 6. CT bit map comparator port map A7 B7 I greater than 6 I equal to 6 I less than 6. A G greater than B, A equal to B, A less than B, end. Generate version, use component instantiation to handle models. Begin start with LSP where LSP is like most bit, C0, bit comparator port map, A0, B0, GT equal to less than IGT of 0, I equal to 0, ILT of 0, C1 to 6 is for I, N equal to 1 to 6, generate C bit comparator port map, AI, BI, IGT I minus 1, I equal to I minus 1, I less than or I GT of I equal to of I LT of I and generate end with MSP where MSP is the most bit C7 bit compared to bottom of A7 B7 I GT 6 I equal to 6 I LT 6 A greater than B A equal to B A less than B and iterative. Generate question 2 nested C all for I N 0 to 7 generate handle LSP where LSP is the rightmost bit. LSP if I equal to 0 generate least bit comparator port map AI BI GT equal to less than IGT 0 IGT equal to 1 IGT is equal to 1 and generate handle MSP where MSP is the rightmost bit. MSP if I equal to 0 generate most bit comparator port map AI BI IGT I minus 1 I equal minus I minus 1 I LT I minus 1 A GT B A equal to B A less than B and generate handle remains bit slices mid if I greater than 0 and I less than 7 generate rest bit comparator port map IA BI IGT I minus 1 I equal to minus 1 ILT minus I minus 1 IGT I equal to ILT and generate and iterative. Summary VHDL data type, VHDL construct language statement, VHDL generate, we can synthesize as well. Concurrent statements appear between the begin and end of an architecture. So far, I've covered the component instantiation statement, block statement not to be covered, concurrent procedure call not synthesizable, concurrent assessment statement for verification. Use this statement, concurrent signal assignment statement, X as assign A and B in or C, some A XOR B XOR C, C out A and B or A and C in and the R B and C in for synthesis. Typically, have no need of using the operator to add direct to the output. X is equal to A and B or C after 5 nanosecond. Used statement, condition signal assignment statement, target waveform 1 when condition 1 else, waveform 2 when condition 1 2 else, waveform 3 when condition 3 else, waveform n-1 and condition 3 n-1 else, waveform n. Waveforms 1 through n are only a single waveform. Compound waveforms are not allowed. When conditions are Boolean expression can be synthesized, but an equation, Boolean equation is better. Used statements 3 selected a signal assignment statement with the expression select target waveform 1 when choice list 1, waveform 2 choice list 2, waveform 3 when choice list 3, waveform n when choice list n can be used, but Boolean equation is better for synthesis. Example 2:1 max said A and not select or B and select. You said A when select is equal to 0, else B with select CL select A when 0, B when 1. Second example, first preferred, you said A and not select 1 and not select 0, or B and not select 1 and select 0, or C and select 1 and not select 0. D and select 1 and select 0. With select 1 and select 0 is equal to A when 0 0, B when 0 1, C when 0 1 0, D when 1 1. Z A when select 1 and select 0 0 0, else B when select 1 and select 0 0 1, else C when select 1 and select 0 1 0, else D. Sequential statements. Sequential statements are like the statement of any procedural programming language. They are executed sequentially according to the control flow of the code. Time introduced using special language statements useful in test benches, HDL code that set up waveforms for input stimulus to your design. Also used in very controlled form for state machine synthesis HDL models. Process statement, process label, process sensitive delete, process declarative part, begin, process statement part, sequential statement, end, process label. The process statement as a whole is a concurrent statement between the begin and the end of a process are sequential like the statements of any HLL. The introduce time into the process, those statements are allowed between begin and end of a process, very useful in test benches. Wait statement, wait, sensitive class, condition class, time class. Sensitive class is equal to on sensitive list, wait on A, comma P, sensitive list equal to signal name, condition class until condition, wait until A is equal to 1, condition, Boolean expression, timeout class for time expression, wait for 20 nanoseconds. Major sequential statement, the next few statements are similar to their counterpart in the procedural language such as C, if statement, if condition, then sequence of statements, else condition, and then sequence of statement, else sequence of and if A equal to 1, then Y is assigned Q, else if B is equal to 1, then Y is Z after 4 nanoseconds, else Y is equal to 0 and F. Sequential statement, case expression is when choices, the sequence of statement, end case state is when 0 0, state 0 1, when 0 1, state 0 1 0, when others state 1 1, end case. Loops for loop label, iteration scheme, loop sequence statement, end loop label, iteration scheme, while condition or for loop parameter specification. Loop parameter specification is about identifying and useful in test benches, but limited use in models to be synthesized. Loop while A not equal to 1, loop sequence statement at least one such A end loop. My loop for I in 1 to 100 loop sequence statement in my loop for op in op band and to move loop. Again, useful in test benches, but not successful. Next statement, next loop label, when condition, if the condition is true, process termination of the current iteration of the loop and the start of the next iteration. Exit statement, exit loop label when condition, cause exit from the loop when the condition is true. Example for a I in parameter range loop, statement 1, statement 2, next when C is equal to 0, exit when Q is equal to 1, end loop, A is equal to A plus B. Possibly D flip-flop, entity Y is port clock reset D in bit, Q out of bit, and Y. Architecture X of Y is entity add signal clock reset D in Q out, and TD reset and TD in are constant. Begin. Process clock begin if clock is equal to 0 and clock event. Then if reset is equal to 1, then Q out is equal to 0 after TD reset. Else Q out is equal to D in after TD in end date in process index. Summary: VHL concurrent station, sequential statement, and VHL example. Thank you.